Hey, what's happening, guys? Here is another gem from my auction score. This is the GW Instek GFG8219a. This is a function generator with sweep and modulation. It is an analog function generator, and we'll go over the difference between an analog and a digital function generator later. But let's just real quick hit on the high points. It is 0.3 hertz to 3 megahertz over 7 ranges, 10 volts peak to peak, 50 volts impedance. It's got minus 20 decibels of attenuation, minus 5 to 5 volt DC offset, 20 to 80% duty cycle, 6-digit LED or LCD, LED, I can't talk again, LED display, and the range accuracy is plus minus 5% at 1 hertz at 3.0 position. Good, not good, I don't know. It's an older unit. I'm guessing, I don't know, somewhere around early 2000s. We'll find out more when we get inside. So right here we have our different decade controls for the frequency, and then a fine-tune control here. The fine-tune control also pops out to activate the sweep. Then we have the sweep time control, slow, fast, in is linear, out is logarithmic. We have our modulation depth and sweep rate, in is FM, out is AM. Duty cycle adjust. Now you'll see on the back this has CMOS and TTL outputs. We have adjustments for them. We have a DC offset, amplitude, and you pull that out to adjust your attenuation. External modulation, internal modulation, gate time, square wave, triangle wave, sine wave, and that activates the attenuation. I do get asked a lot by folks who, you know, when they see the video, they say, but why would I want to buy one of those? Well, there's a lot of reasons you'd want a function generator, especially one that has this many features. I mean, just off the top of my head, you use it for troubleshooting. You can use it as a bias or a signal source. You can use it to test amplifiers, test logic circuits, test speakers, test networks. There are a lot of different things you can do with a function generator. Let me show you. Let's say you want to test a piece of audio equipment and it's not sounding the way it should. The function generator you set up to output a square wave. So you know that's what we have here, a square wave. You send that through the equipment, you put your oscilloscope on the other end, and what you get out say looks like this. Well, what you have here is frequency distortion, a low frequency distortion. Or if it looks something more like this, then you have some harmonic fundamentals that are getting on there. Or if it looks more like this, then you have a phase shift. Or if you see something that looks like this, in that case you have a high frequency loss. Something like this. Then you end up with some oscillations. You know, there are a ton of things you can see, and with a little bit of experience you can learn what those waves look like, what they mean, and how to interpret them as to where they come from. So that's one of the great uses of a function generator. Okay, we examined the front panel. Now let's look at the back panel. We have an internal or an external counter source. We have our TMOS TTL output. We can do a voltage controlled frequency or our modulator input. We have another GCV output and a counter input. So this could actually be used as a counter. We have our IEC, and this is a fused holder. and a universal power source for 115 or 240 volts. So I guess our next thing to do is to open this up. And when we find the right spot, we can pull out the handle. Now all I got to do, I believe, is remove one screw. Let me get in here and do that. My home work surface is not conducive for taking apart large pieces of test equipment, so I'm sorry, bear with me. Get this apart here. Thought that was all there was to it. Alright, be right back. These are like split ring. Wish I was at the school where I had access to a pair of split ring pliers, but I don't. Maybe these will just pop out. Yeah, they're just plastic. Okay. So once I remove these, the cover should slide off easily. And then we can have a look at what's inside, right? There we go. Ooh, that is absolutely full of goodness. All right, so we see three what appear to be daughter boards here. So now these two here, I'm pretty sure are for the sweep and modulation, which was an add-on for this. And this one here connects directly to the frequency counter. So that's probably, yeah, a frequency counter board. Let's see if we can make out what these chips are. Let's zoom in here a bit. All right, LM, so say 324N, that's a op amp, quad op amp, I think. And this one, MC1496, is probably a modulator, demodulator. All right, let's see what we got going on over here on this board. Oh, CD3046, this is a Darlington transistor array. Those little guys are probably op amps. What's this one here say? I can't hardly read it. Oh, it's another op amp. Now over here on this main board, they've got their own chip. You got a 740000. That's a quad input NAND gate. I'm not real familiar with these MCP chips. This one, this PF2480, I'm not sure of that one either. What the heck is this one? I can't even see it. Alright. MCD something. Hard to read. So those are the daughter boards. So we have our frequency board, our modulator and sweep boards over here. And the actual frequency generation unit is probably on the main board. And this is a separate frequency counter board. Now, one thing to notice down in here is that the power switch is an actual switch. So that's pretty nice. Let's see if we can't pull out one of these daughter boards here. Doesn't want to come out. Have to go to the big end. There we go. See what's hiding underneath. There's a couple more little op amps down in there. Well, this thing is full of op amps, and I'm surprised I'm not seeing a decade counter in here somewhere. Be careful, I don't want to break this. That guy didn't want to come out. Nothing but passes under it anyway. So that's a pretty good look at what we got going on inside. Let's put it back together and check it out. One thing to note is I was a little bit off on the date. I thought this was early 2000s, but I found a date code on one of the ICs, 9944, or is that what it said? 9944? So this is from the 90s. That's not on right. We'll be right back. Okay, I've had it up and running here for about 30 minutes or so, give it a little chance to warm up. And you can see we are in the 1K range, square wave, and the frequency is all the way down. And it's giving us a reading of 9.44-ish hertz. But if you look up here on the scope, you can see we're getting a reading of a solid 9 hertz. So it looks like while the analog frequency generator in that unit is putting out a good solid frequency, the frequency counter itself is nowhere near that good. So let's increase the frequency here. Go up to the max for this range. And we'll adjust the oscilloscope. The square waves are solid and they are just a little bit noisy. And we're seeing, what, 3.285, let's call it 3.29 kilohertz. And it is showing us 3.2855. So it looks like it's more stable in the upper ranges. Let's go up to the 10K mark. So we're at 33 kilohertz, 33.5 kilohertz. And again, the scope is showing us 33.5840. Well, if we turn it down to the lowest point in this range, oh, it's just the frequency counter is jumping all over the place here. Seems to have a lot of drift to it, while the analog frequency generator itself is pretty stable at 96 hertz. Let's go up to the top range here, to the megahertz. So I'm seeing about 11K here at the bottom, 11.4. And we're seeing 11.42 on the oscilloscope, but we've got some serious jitter there and a lot more noise. That's at the lower range. Let's go about halfway up. Then we'll bring the scope in here. Now we've got a decent lock there at 1.7605, and you can see on the frequency generator 1.75. So that's looking good, although our square waves aren't so square anymore. The rise time is a little bit off. And if we go up to the maximum, we're seeing 3.255 megahertz, and on the scope 3.255. So while that looks good, the square waves themselves have kind of fallen apart. Let's go to a sine wave, and the sine wave looks pretty good. Again, at the 3.24, it's showing us on the frequency generator, 3.24 there. So it is somewhat acceptable, but definitely not exceptional. Now, the one thing I want to try here, let's go with a medium sweep time linear linear, sweep time, medium time, and we'll turn the sweep on here. Not really seeing too much going on there. I might not be doing it right. Like I said, I'm unfamiliar with this. All right, let's go with the slow sweep time. Am I messing something up? How about a logarithmic sweep? Again, I'm seeing absolutely nothing from the sweep. All right, what about modulation? Let's go with FM modulation. Modulation on. Oh, this is the sweep rate. Okay, I did not have the sweep rate on. It was my fault. All right, so we're seeing some FM linear modulation. Let's turn the modulation off, and we'll turn the sweep back on. Okay, now we're seeing sweep. That was my bad. All right, let's go with AM modulation. I'm not seeing any amplitude modulation. I'm seeing frequency modulation. Let's slow the rate down. Maybe I'm missing something. Okay, there's amplitude modulation. And there's frequency. I just had the switches backwards. All right, so yeah, it's okay for a mid-90s frequency generator. It's not fantastic. And I think one of the things we're going to find is this frequency counter is just completely out of whack. Now, I said earlier I would show you the difference between an analog counter and a digital counter. So let me set that up and we'll come back and I'll show you the difference. All right, here's my digital frequency counter. This is the Fieldtech FY2300. This is a 6 megahertz arbitrary function generator. And you can see here that we are using channel 1, sine wave, 10 kilohertz, 0 offset, 50% duty cycle, 10 volts peak to peak, no attenuation. And if we come over here and look at the scope now, you can see very clearly that we have a nice solid signal. This is the hardware frequency counter down here, 10 kilohertz. Very, very little jitter, very little noise. And even as I adjust it up, you know, everything stays copacetic. We're at 420 kilohertz hardware counter showing 420.08, we'll call it. We're getting 420 there on the software counter. So everything is really nice there. And one of the other differences is, let's slide back over to the digital arbitrary waveform generator. If I go through wave here, square, triangle, ramp, negative ramp, square, or stair. I mean, look, the analog frequency generator just can't do that. So that's the difference between the technology of today and the technology of, what, 23 years ago. There's just a lot more you can do with a digital frequency counter than, or frequency generator, than you can with an analog. So while I got this from that auction full of equipment, and like I said, yeah, I got about 20 pieces for $100. So this cost me $5. It's definitely worth $5. Maybe, you know, if you don't have any other equipment, it's probably worth 40 bucks or so. But I wouldn't be paying any more than that. I would call this definitely a very low-end piece of gear, but still a very functional piece of gear. It is, you know, you saw the insides. It's all through-hole technology, resistors, capacitors, transistors, a few ICs. If there's a problem, you can definitely hunt it down and change the parts. Whereas with this, you know, there's a microcontroller in there and a lot of programming going on. If this thing breaks, yeah, you're probably going to be in for buying a new one. But anyway, that is a look at the GW Instek GFG8219a function generator with sweep and modulation. I hope you guys enjoyed this. If you did, give me a thumbs up. Feel free to comment, share. Don't forget to subscribe, and a big thank you to all my patrons. I wouldn't have been able to buy this auction stuff without the patrons, so you made this possible, and a big thank you. That's it. I'm out. Peace.